So, in the questions that we've been asking about composites, we went on to a final question where we would like to spend most of the time in this whole course, which is how to model the flight vehicle structures, the materials and the geometry put together. And in particular, we want to look at composites and look at metals as a special case, as long as the stresses are all within the yield stress for those metallic alloys that are involved. So this is a set of pictures that we saw in the previous class, and just summarize what we discussed as part of it. This is the traditional approach of how composite structures are analyzed, and there's a lot of parallel with what is done in the case of the metals. As far as the lower length scales of micromechanics is concerned, that is something that in the case of the metallic alloys is typically done by material scientists who work at the crystalline or granular levels to understand how the individual metals which form part of the alloy eventually contribute towards that. But most of the properties in any case are determined experimentally. So it's mostly at the research level or for developing newer types of alloys, etc., that the material scientists' approach of looking at designing new materials based on the microstructure becomes very critical, right? So as in the case of composites, we will see that this plays as much of an important role as the larger length scales, that we need to understand from the fiber properties, the matrix properties onwards, all the way to their volume fractions, to bring it to a certain single layer, and then stack up those layers and then make different shaped parts out of it, eye section, beams, cover skin, etc. So all those kinds of parts are all built upon this, and the information, as I said in the previous class, typically transfers from the lower length scales up to the upper length scales. So in today's class, we will try to focus on this. This is a subject by itself. In fact, until one of our colleagues left, there used to be a separate course on micromechanics itself, an entire 3-credit course. Now we don't have that, but there are lots of good books which are associated with that. But we will not go into all those details beyond the scope of this particular course. What we will focus instead is on the simplest models that are available, and we'll look at some sample examples of how the improvement can be done over those simple models without going too much into their details. We'll see what are the factors which affect those improvements, and in what way we could probably have a better, more reliable estimation of the properties. The whole purpose of this, as well as this, is to come up with a fictitious material which is going to behave exactly in an overall macro sense similar to what the actual composite behaves, because the actual composite is heterogeneous. It has different properties at a material point which is within the fiber, a different material property at a material point which is in the matrix, and perhaps a different material point in the interface points as well. So we do not want to go into that complexity, because it's the scales that we are interested in of the order of a few meters. This is of the order of a few microns, and to translate from here to here as it is computationally almost impossible task. You could do it for smaller components or smaller specimen, etc., using some of the best computational resources that you have. But when you can do a reasonably good job without having to look at this heterogeneity as it is, then why not take advantage of that? So that is what this does. So this essentially takes up one particular unit cell and then stacks it up into a set of them, which constitutes a representative volume element, which behaves almost similar to the overall composite, and then we try to get the properties of that. So that whole process is called equivalent homogenization. So in other words, starting with a heterogeneous material distribution, and you're going to something which is homogeneous, which is equivalent in its behavior. What does equivalence mean? That means if you apply certain stress on this at its boundaries on this structure, and the strains that result out of it See, in general, you could have all these 6 stress components which are excited by certain kinds of loading, and then you measure the strains at different locations. You should have the same result in an overall averaged out sense. In reality, you will not have that because the stresses within the fiber and the stresses in the matrix are governed by different material equations, what we call as the constitutive law. But if you take it in an averaged out sense, that is, let's say this whole thing is a representative volume element, then I take the actual stresses and strains in each one of these, the different components of them, and I integrate them over this volume and divide by the volume. I get a volume averaged stress for the 6 components. Similarly, for the 6 strain components, that should be exactly same with your equivalent homogenized materials. That's essentially what we are trying to talk about. Now, that is to take up a unit cell or a representative volume element to be more accurate, and then you're trying to homogenize that. Once you're done with that, you get a certain layered properties which are anisotropic in nature now. Even if the fiber by itself was isotropic, the matrix by itself was isotropic, but the end result of putting them together makes it anisotropic. But in reality, you see that many fibers are also anisotropic by themselves. In other words, the property along the longitudinal direction and the transverse direction are quite different from each other, and you need to account for that. But there are also examples of materials or fibers which are isotropic as well. So many initial chapters in textbooks, etc., on micromechanics would assume the fiber to be an isotropic material, just as the matrix is also an isotropic material, irrespective of whether it's a polymer matrix, a metal matrix, or a ceramic matrix. You typically take that matrix almost always as an isotropic material, but the fiber also can sometimes be isotropic, in some cases anisotropic. Now, exactly what we did here, that equivalent homogenization, is what we do at the mesomechanics level also. Depending upon how fast I go, we will see some little bit of a sample of this, and then take it forward to the next class probably, and then eventually we'll look at this kind of a stacking and what it leads to. Again, here also, just like what we did an equivalent homogenization with the fiber matrix level, here we do an equivalent homogenization in the thickness direction, here marked as Z coordinate. So along Z, we integrate the properties and divide by the thickness to put it in a very crude sense, and to get, instead of these different layers, different properties, you get a single thickness of the same thickness, single structure of the same thickness, but composed of, again, a new fictitious material, which will behave in an overall sense just like what the actual composite, which is heterogeneous in this direction also. It's heterogeneous at the microstructure, it is heterogeneous at the laminate level across the lamina, which could be at different angles. Sometimes you could have hybrid composites where each of the layers might have different fibers. Sometimes only the top and the bottom might be lamina like this. In between, you could have a core to make it a sandwich. Whatever it is, there is a way to integrate over the thickness the various properties and come up with an equivalent material. Instead of having separate core and the face sheets in the sandwich, you would have a single layered structure of the same thickness, which is having similar or identical, rather, equivalent properties. So as I said, the macromechanics, unlike the micromechanics, is something that you're familiar with, even with metallic structures, what you study in strength of materials, etc., as beam models, and or a little more advanced courses as plate models, etc. Those are shell models. Those are all eventually macromechanics, and it doesn't matter whether you're dealing with a composite or a metal, you'll do things in a very similar manner, just that the inputs will be a little more complicated because of the anisotropy that is involved. So again, mesomechanics is something that you do not do obviously with metals unless you have, let's say, a bimetallic strip or a multimetallic strip. So then you could probably have something like that in certain structures, but otherwise you really don't need to deal with that. So as I hinted in the previous class, this is as far as the traditional approach goes, but for more research-oriented approaches, or where you want to look at the design from a very fundamental perspective to try and see how for future designs there could be improvements, etc., you tend to push the information in the backward direction also, from the larger length scale to the smaller length scales, so that then in small areas of interest where, because at this level you know how the stress distribution is going to be, how the displacement distribution is going to be in all the directions, and then you could identify certain pockets which are stressed the most, or it could be having very large displacement and or strains, and then you try to focus on that particular area, go back to the original structure and what we call as the substructure analysis, and try to identify what's happening within the fiber matrix and the interface, and see if you can improve certain things. For example, how it changes with the volume fractions, how it changes with the coatings that you give for the fiber. You could also probably have other additives in the matrix. Sometimes, for example, these might be continuous fibers. In the matrix, you might have a small percentage of carbon nanotubes or something like that. So how does that affect? So depending upon how, of course, the spread is done in terms of the volumetric spread as well as orientation control that you have, it might end up with a matrix which is also anisotropic. So you have to obviously take that into account when you do the micromechanics, etc. But just be aware of this fact. We are not going to go into that part of in this course where we take it backwards to the lower length scales. Yes, please.
Sir, how are the micromechanical properties actually measured? Because at that level, I mean, what is the nature of the measurement? Because probably on a macromechanical level, we can always do an experiment.
Correct, right. So it's very challenging. So it's not your regular typical structural mechanics labs which can do it with the UTM machines, etc., that they have. Instead, there are very sophisticated machines. The concept is very similar, but essentially you're trying to, for a given load that you're applying, you're trying to measure the deflections that are there, and then you're trying to work backwards to calculate the strains, etc. There are also optical methods where you try to project and see what is the change in dimension that is happening, etc., so that you can get even to the true stress rather than the apparent stress with the original cross-sectional dimension. The advantage we have is that amongst all the properties, the longitudinal properties are the ones which are more dominated by the fiber. And the longitudinal properties are the ones which are much more easier to measure, relatively speaking at least, compared to the other properties. The other property, most of the other properties are dominated by the matrix, which anyways like you test like any other isotropic material, so homogeneous isotropic material, so there's not too much of a problem over there. But we have to rely sometimes on a backward approach where you have the fiber and the matrix based on a reliable micromechanical model. You know the properties of the matrix, you know the properties of the composite, then you try to arrive at the fiber and then use that for other general designs. So there are many different approaches that they go through. There are also, just like we have let's say an Euler-Bernoulli beam model or a Timoshenko beam model for a beam, we can arrive at theories over and beyond what we are going to look at today. We are going to look at the simplest, which is rule of mixtures, but there are a little more advanced approaches where we deal with these just like that we will deal with this. We will take a beam made out of this, which is a representative volume element, and then try to apply certain loads on that and try to see how it behaves. It's essentially a computational experiment that you're trying to do, and out of that you try to arrive at certain overall behaviors of the stress versus strain, from which you can get the moduli, the Poissons ratios, and the shear moduli, whatever. Typically for shear, you try to do what is a torsion test, because you can't directly measure those changes in angles, and torsion constitution is one case where you can have a pure shear kind of an example. You can either make a circular tube made out of these materials, first just out of the matrix alone, and then out of the composite, and then work backwards to get what is the effect of the fibers on that. Now, if you actually look at how this is going to be, so the simplest representative volume element you could have is like this, where so you have something like this. So then you have the fiber properties and the matrix properties. So what you could do is, with this, you essentially come with a UD tube that you have, and then you so you have a tube like this, which is consisting of those fibers, and then you apply a certain torque on this. You could fix one end, then you measure the twist at the other end, and based on that you work backwards. So one you make with the fibers in it, which is a composite, and the one without the fibers, which is just the matrix, and then you could use those two results to work back to understand what is the contribution that the fiber is making. So this is one typical approach you do to get quantities like GLT, which is the shear modulus in the LT plane, because L is along the length and T is perpendicular to that, and your shear stresses when this kind of a thing will be resisted by, if it's a thin walled beam, essentially shear stresses like this, which are on your X, which is along the length in the theta direction. So you can think of this using cylindrical coordinates as tau x theta. So using that, you work backwards because you can get the GLT for the composite, you can get the GLT for the matrix, and then you try to work out the GLT that the fiber has based on your micromechanics models. So these are ways of working around that, but there are also certain ways in which these are done in an experimental level at the fiber level, but extremely sophisticated equipment are required in order to for that approach. Yeah. So typically, once you do a few validations with this and you're satisfied with the reliability, you don't need to go for those more expensive approaches. You could do it using the modeling approach. So it's all a question of establishing the reliability of your models. One, start from very rigorous physics, use state-of-the-art mathematical tools to arrive at your models, and then experimentally validate it for a few cases. And then once you're satisfied, then you start using the model to predict the fiber properties. So you typically, this whole process is used for equivalent homogenization, but it can be used the other way around to get to the fiber properties from the composite properties.
Sir, even the measurements, even if we go for optical and all, generally only a surface measurement.
Yeah, yeah.
Then, and for a composite, very likely on the surface it is going to be a matrix only. Probably the fibers will be inside
Yeah,
it.
yeah.
So how do we get those strains generally?
You mean the strains in the fibers? So that is not typically in a composite. It's almost impossible to get direct measurement of that. There can be certain embedded optical fibers, etc., which can give you the signals from which you could do. But if you're using the regular conventional structural fibers, even if it's glass fiber, etc., it's not of the optical fiber quality, then you obviously will have to live with the modeling approach to work in a reverse engineering to get to its properties rather than directly measuring it. It's not that they're not there, just that it's very niche, and it's done by very, very few people and labs, and involves very expensive equipment. So it's not a run-of-the-mill thing that you need to do. So it's more when it's of a concern to improve the fiber properties, so which means that how the manufacturing process for the fiber itself in some terms of, let's say, an extrusion process, etc., or the temperature pressure control that you need to do while doing that, etc., or the raw material that you start with, you want to improve. Let's say in the case of carbon, for example, you start either with rayon, pitch, or pan based precursors. So which of them works better? Within them there could be so many other types, how you work out. So when you're doing those kinds of material development, that's when you need a much more accurate way of determining it in a direct fashion, rather than depending upon these models. And that is also one of the reasons why these fibers, etc., are made, at least for the aerospace grade, are made by very few companies, because they have to have a long-term plan in terms of their research to see how they could develop these materials, and huge investment in the initial infrastructure is required in terms of the equipment, and also the skill sets of the people who are testing that. So the affordability of both the human resources as well as the equipment makes it kind of difficult for new companies, let's say a startup or something, to get into it. But because it requires a large initial investment, which if the investors are willing, maybe it's possible, but typically it's done by very few companies around the world, and which is why they have almost a monopoly, or some kind of similar to a monopoly over certain types of fibers. Yeah, so I think we've finished with this. Let's go on. Okay, so we get on to this topic of micromechanics. As I said, there are many more advanced ways of doing it. We'll not go into all of that. We'll just focus on the simplest possibility. And that simplest model is called the rule of mixtures, as many of you will already be aware of. And to start with, the simplest thing to deal with there, even before we go to the Young's modulus, is to understand that we have been doing this almost on a regular basis with many other problems that we've been dealing with mixtures. For example, if you want the density of a material, let's say a composite, then you typically have the density of the fiber multiplied by the volume fraction of the fiber plus the density of the matrix into the volume fraction of the matrix. And by volume fraction, we refer to the total volume of the fiber in the composite by its the overall composite volume. And similarly, this quantity, the volume fraction of the matrix, is given by the volume occupied by the matrix divided by Vc. So in a few cases, you would have additives, and or if the manufacturing is not good enough, you might have certain voids, etc., coming in. But for most aerospace grade composites, you typically do not have voids because of the kind of stringent quality that is involved with the manufacturing process. So if there are no additives, then it's very clear to see that the small vf plus small vm is equal to 1, because the big Vf plus big Vm is equal to your Vc. So when we add these two fractions, Vf plus Vm becomes Vc, cancels with the denominator, and you get 1. So this is something that we've been very familiar with in calculating the density of a mixture using the density of its components. If there are more components like additives also you want to add, you could have just add one more term, which is your row of the single additive, let us say. Then you have the volume fraction of the additive as well. And then, of course, this would become plus Va. This whole thing is equal to 1. So it's the more components you have. For example, if you want to take care of the coating separately in a fiber, you have the overall geometry, and then you have a thin layer of coating, and you know the properties of that coating as well. you can do it as a 3-material problem, and you could arrive at that. So, but to keep things simple, because anyway the extension to additives is not so difficult, we will take the case of just the 2 materials alone, the major materials that are there in the composite, the fiber and the matrix, in which case we don't need to deal with VM. So essentially we are saying that this is equal to 0 when there are no additives, and so we are saying that your VM, small vm, is equal to 1 minus Vf, small vf. So this is going to be and not an independent variable that you're going to be able to control in your design. Once you fix the fiber volume fraction, you are fixing your matrix volume fraction also. And theoretically, depending upon how you pack this fiber, there is a certain maximum that you can go to in terms of how much, for example, in this whole thing, the diameter of the fiber is equal to the cross-sectional dimension of this. Let's say, let's use the same notations we've been using. The length is L, the breadth is B, and the height is H. And let's say we don't have the coating, which is just a single fiber that is there uncoated, and let's say its diameter is, let's say, some small d. So in terms of that, you can calculate as pi d squared by 4 is the area occupied by the fiber. So that will essentially be your pi d squared by 4 into the length, which is L for both the fiber as well as the matrix, and then you divide by the overall volume, which is your HBL. So that gives you your Vf, the fiber volume fraction, and then using this you get the matrix volume fraction as well. So typically you could see that the reason why I was trying to explain this is the maximum you could go with D is to make it equal to your minimum of B or H, whatever is that. So if you take it as a square where H is equal to B, then your diameter is equal to H equal to B is the maximum that you can go with this type of a stacking that you have. But you can prove purely a geometric exercise that if you have it as a hexagonal arrangement, then you would arrive at the maximum theoretical possible limit for the fiber volume fraction, and therefore the minimum for the matrix volume fraction over there. Leaving all that aside, typically in aerospace composites, the approximate value for this is in the range of 0.4 to 0.6, depending upon the how severely that structure is loaded. So you would want to go to 0.6 or a little beyond that, typical cases where the structure is heavily stressed and the material is heavily stressed, therefore. So whereas to save the cost, because in this whole mixture, the fiber is the more expensive thing compared to the matrix. So if you, in large volume productions, you might want to operate more at the 0.4 level, so that you're essentially using less amount of fibers compared to the matrix. Yes, of course, the properties will slightly drop, but you're willing to live with that for the cost savings that you would eventually incur because of that. But this is the typical range, though for theoretical purposes we'll be looking at much larger ranges, because you could go from 0 to 1, where once you have a model, there's a way to check for whether you're got a model correctly. One of the initial checks you typically do is to go to these extremes, because when you go to 0, that means Vm is equal to 1, or in other words, entire thing is matrix. You know the matrix properties. Your equivalent homogenized properties should give you back the matrix properties. That is one check. Whereas if you go to the other extreme of 1, then obviously you're going to have Vm equal to 0. It's all going to be all fibers, and so your model should also lead to whatever the fiber properties are. So, so it's purely for such theoretical tests that you want to do, or computational tests that you typically plot versus fiber volume fractions of that range. But for most practical purposes in aerospace, you could have in this range. In some even low cost applications like automobiles or a few other applications, you could have even lower fiber volume fractions. But there are also lab tests which are done with the hexagonal kind of arrangement that I talked about, where you try to push the limits from towards closer to the theoretical limit to see what exactly happens. It's also a question of once you make it more and more closely packed, the stress transfer between one fiber to the adjacent fiber is going to become more and more difficult, because the stress transfer essentially should happen through your matrix. Even in the simple example that I talked about, where you have the diameter and the breadth and the height the same, you could see that the very next fiber is also going to be like that. In other words, the fibers are touching each other, stress transfer becomes much more difficult. The way the stress transfers between two fibers is not very good, which is why a bunch of fibers we saw is good only for tension. It could be like a rope or a string, let's say a hanging bridge or something like that, where you could use just rods or fibers. But once you have the matrix, it uses its shearing properties in order to transfer the stress from one to the other. When you have different levels of stress in this and this fiber, that transfer is very, very smooth once you have a reasonable layer of thickness of matrix between two adjacent fibers that you have. So this is but of course, in reality, you're dealing with not individual fibers, but even toe and things like that. But even there's an infusion which takes place through the process that you're having within the toe, between the fibers. Between one toe and another toe, there might be a much bigger gap, relatively speaking, compared to the gap between individual fibers within the toe. But you still have a certain level of gap, and that enables the stress transfer. Also, along the length, if you have too many fibers like this, there could be, let's say, certain locations where they are touching with each other, but the same fiber at some other location is not touching, and therefore there is a possibility of stress transfer taking place through that. So this is not such a severe requirement as long as you are dealing with these continuous fibers. Again, in the case of short fibers which are randomly distributed, once again, you could have sometimes a bunch of fibers which are touching each other. But depending on the loading situation, sometimes either the matrix-rich region over here where there are no fibers could be the critical thing, or if you have too many fibers bunched up over there, because of the way the shear cannot be transferred, sometimes for certain types of loadings, you could have that as the critical. So more or less, to whatever your manufacturing process allows, whether it is a continuous fiber composite or a short fiber randomly distributed composite, you would want to make sure that these pockets rich in either one of the materials are avoided as far as possible. But some cases you do actually bring in. We saw an example of that where we had a large number of fibers, and then we were dropping a few layers. Let's say this layer is dropped, and then you have just two layers over there. So in those regions, you might sometimes have small matrix-rich pockets, but the design has to take care of the fact that the stresses in certain loading conditions can be large, and how do you account for that? Sometimes, for example, you could have certain reinforcements which are of a nanoparticle kind of a reinforcement over there to ensure that this transition is smooth. In smaller regions, it's more easy to control the distribution, both in terms of the volume as well as the orientations. So you would go with that kind of an approach. Now, let's come back to this particular equation. Let's so here we take, let's say, thanks. So we talked about this model where we have a breadth B, a height h, and a length L, and this is the fiber. So all properties of the fiber will denote with the subscript F, just like what we see over here. And then this is the matrix which you have over here. So now, whether you have this geometry or not, there are certain models which are immune to it, and you might want to take advantage of that fact and arrive at a simpler way of looking at this whole thing. So instead of going to the actual fiber geometry, you could just treat it as, because if you are having a case where you want to determine the longitudinal modulus of this, this is defined as if I apply a certain level of stress on this, which is, let me introduce also the coordinate system. This is x1, x2, and x3. And typically, this x1 is also along the fiber direction, parallel to the fiber direction. So sometimes it might be referred to xl, which is the longitudinal direction. And these two are both transverse directions because they are both perpendicular to the fiber, x2 and x3. So to distinguish between them, you might want to call one of them as xt and the other as xt prime. So t and t prime are both transverse directions, but they are mutually perpendicular to each other. So that is to be accounted for. So this load that we are applying is essentially your sigma 1, or you could call it as sigma LL that you're applying to the overall structure. So that overall structure is the composite. So we could denote it with a superscript C to say that it is happening on the composite. Now, whether you have a circular geometry, or let's say in this particular example, of course, this needs to be fixed. Just like you can think of it as in an UTM, where one end is fixed, the other end, the load cell is there applying the load, which is an axial load, which is pulling it by a certain amount, and then you're having that. So it's very clear that irrespective of the actual geometry that you have, let's say this is the fiber, I'm hashing it in this way, and the matrix, I'm hashing it in this way, then I can just take one of them as the matrix like this, and this as the fiber. As long as I have the same volume fractions, it just doesn't matter for this kind of a load where I'm only interested in pulling it in this direction and measuring the strain in the same direction, because we want this essentially the strain along the longitudinal direction to be able to calculate this Young's modulus, which is EL of the composite. So unless otherwise stated, it is of the composite. So superscript C. Whereas these are specifically mentioned as the fiber and the matrix over here. We are allowing for the fiber by itself to be anisotropic, which is why it's important to mention that this is the longitudinal modulus of the fiber rather than its transverse modulus. In other words, your ETF and ET prime F could be equal to each other, but will be different from this quite a bit. So there are fibers like that. So you have to ensure that you're feeding in the right input to calculate the properties of the composite that you want over there. So now that you apply your sigma LLC, or you can think of it as applying a certain force on the composite, which is your FC, of course, in the longitudinal direction, which is nothing but the composite that you have. So you, let's say your breadth and height are still B and H overall. So the area of cross section on which this stress is acting uniformly is BH. But in reality, in the actual composite, heterogeneously, the stresses in the fiber and the whatever you have over in the matrix could be quite different from each other. But here we are saying that we make certain assumptions in order to derive that. As I said, this is the simplest model. So There could be certain assumptions which are questionable, but we try to understand this in a much bigger picture point of view to understand how the individual components of the mixture or the composite are contributing towards that. When we are trying to do that, we say that when we are applying this force, in reality, it is possible that the fiber and the matrix might extend by different amounts. But if the bonding is, let's say, ideal, perfect bonding, what we call, then we say that the fiber and the matrix, or the whole composite, move by the same amount. So you start with an L initially, then it becomes an L plus delta L, right? And then you could define the strain, which is gamma LL, as that change in length divided by the original length that you have. Let's see, let me use the small l itself. Yeah, so that is a linear problem where you're considering geometric linearity. Similarly, we will replace this in terms of its Young's modulus for the composite, which is what we want to determine, EL for the composite, multiplied by the strain in the composite, which is your gamma LL. This is whether it is the composite or the fiber or the matrix, because delta L is the same, L is also same. Therefore, whether I use superscript C, F, or M, it's always going to be gamma LL. So I can drop as well the superscript. It doesn't matter. So in all cases, it's going to be the same. Now, that is equal to your delta L by L. And so this is going to be delta L by L. Now, this force that is acting on the composite as a whole has to be partly taken by the fiber, it has to be partly taken by the matrix. So in other words, I can write this as FLC equal to FL fiber plus the FL force in the L direction that is taken by the matrix. Okay? So just like what we did with the composite, the same thing we can do with the fiber and the matrix as well. And let's say this, the only difference is in H, because B and L are the same for both the fiber and the matrix if we go from this to this. So this is an assumption that from this to this, it's not going to make a difference. You can actually verify that also by using what we calculated as the volume of the fiber, pi d squared by 4 multiplied by L, etc., and then subtract that from B into H to get the matrix area, yeah, and you do it, you will end up with the same thing. So in this particular case, so you can see that it is a valid simplification to go from this to this and say that as far as this problem is concerned, where you're applying only a load along the longitudinal direction and you're interested in measuring only the strains along the longitudinal direction, these two are equivalent to each other. But that test you have to do each time when you're trying to determine other properties of the composite, whether this kind of an equivalence is really valid or not. So that is one test you typically have to do. Now, we have this. Now, your FL in the fiber can be written as, using the same approach, you have, this is equal to sigma LL in the fiber multiplied by its B into HF, where I'll call this as, let's say, HF, and this as HM, this is the matrix and this is the fiber that you have, right? So sigma LL, so that is the first term over there. Similarly, you have the second term, which is your sigma LL in the matrix multiplied by B into H of the matrix, the height of the matrix. And in both of them, I can substitute in a similar way what we have done with the Young's modulus into the strain, and the strain is the same in both cases. So I can, instead of sigma LLF, I can write it as EL of the fiber. And also you have to be careful that it's not only the direction, whether it is transverse or longitudinal, but in the longitudinal itself, there's a difference between how it could behave in the tension and the compression. So whatever we are doing, I'm not specifically mentioning over here, but if you could use a notation associated with tension, that's also appropriate, because tension is usually T, and you also have the transverse direction T, so you're not specifically mentioning that, but be aware of that. So that is EL of the fiber multiplied by gamma LL, which is the same irrespective of whether it is fiber or matrix or composite. So that multiplied by your BHF plus your other term, which is going to be EL of the matrix, EL of the matrix multiplied by B into HM, along with gamma 11, of course, gamma LL. Okay, so now you can equate those two and cancel out all your terms, and you would see that in this particular case, your volume fractions VF is equal to HF into BL divided by HBL, which is the overall volume of the composite. Similarly, of course, VM, you can just get it as 1 minus VF, but essentially it is equal to HM divided by H, just like this is equal to HF by H. So once you cancel out all the common terms on this, it's very easy to see that you can substitute for VF and VM as nothing but your HF by H and HM by H. You replace it through the volume fractions, you could see that this equation can easily be derived. Other things getting cancelled, including your gamma LL, because that is the same length change in length as well as original length that you have, because of which that also gets cancelled on both sides, and you end up with this particular formula that you have. Now, is this clear? Any doubts on this? Okay. Now, if you plot this particular equation, Young's modulus of the composite in the longitudinal direction versus the fiber volume fraction, you know that the theoretical limit is 0 to 1, but in fact the theoretical limit based on the packing factor would be even lesser than 1. But just to compare it with what happens in a sense of just testing the formula for what it is. Even from the equation itself directly you can check if I set, if I have only fibers and therefore this is 0 and therefore this is 1, it's very easy to see that EL becomes ELF at one extreme, so that is what you would have. So let's mark this as EL of the fiber. So then, so you would have at 1 a point over here which represents the fiber property itself. Similarly, when the volume fraction is 0, you have it equal to the longitudinal tensile modulus of the matrix, which is isotropic, and therefore I can drop off this subscript that I don't need to specifically say L over there. So that is usually a much smaller value. We saw certain examples where how different from these are. Let's say it's an epoxy matrix and carbon fiber. The moduli are very, very different orders of magnitude from there, and therefore you have this. But if you're plotting versus VF, and this is, let me so let that be VF itself. So this would be one minus VF. Now you can see that this whole equation is linear in VF. So now that we have 2 points on this, it's very, because at 0 it should go to this. So those 2 points should lie on that straight line. So it's very easy to see what this behavior would be like. So it's very clear to see that, so of course you would typically be operating in a 0.4 to about 0.6. So what would be of practical relevance to you is just this portion of the curve to see how the variation could take place. Now, shortly we will also see to calculate not only the longitudinal modulus, but also the transverse modulus of this same composite using the same kind of a model. Now, whereas this works very well for most composites, the one that you calculate using the transverse modulus for the composite using the transverse modulus for the fiber and the matrix could be quite different. Now let's take a simple example where the fiber is not anisotropic. In other words, its Young's modulus in the transverse direction, whether it is T or T prime, is the same as that, just like what we did for the matrix. If we didn't need a subscript L, suppose we have a case of a fiber whose tensile modulus both in the fiber direction as well as perpendicular to itself, which is very difficult to test. So we can say in some cases that is equal to each other. So then these 2 points will still remain the same. But we will soon see that the behavior of ET, when we calculate that ET for the composite, it's not going to be the same. In other words, not in a straight line. And in fact, you would see that if you plot this, this is how that would look like. Now, many of you, irrespective of whether you are from, let's say, a mechanical background or electrical background, would have looked at springs in series or dashpots in series or parallel, and then resistors, inductors, etc. in series or parallel, capacitors too. So then you arrive at certain results for that. So this is very similar to that your, this is what we are plotting here is EL for the composite, and this is ET for the composite. Okay, so we're plotting both on the same curve. And you could see that, so whereas this follows a kind of behavior based on the assumptions that we have made, that it is going to have this kind of a linear equation. The other one is essentially going to be a reciprocal kind of a relationship. In other words, your ETC is also going to be dependent on your, so this is 1 by ETC is equal to VF by ET of the fiber plus the volume fraction of the matrix by, it's of course the same, it's isotropic, we are assuming this to be. So let me keep this over here, or we could use the subscriptium over here. So it's the matrix. Yeah, we will derive that. We will see why that is happening. So this is very similar to whether you have, let's say, 2 springs of spring constant K1 and K2 either in series, or you have it in parallel to each other. So the net spring constant is going to be different from each other. So we will come to that. We will derive that. We will come to that. But once we derive that, if we were to plot this versus the fiber volume fraction, again taking Vm as 1 minus Vf just like this, in other words, no additives, no voids. So therefore, once we plot ETC versus Vf, we will get this kind of a curve. In other words, for a large range of the fiber volume fraction, including within 0.4 to 0.6, which is of practical interest to us, the fiber hardly contributes to the transverse modulus. In other words, this is a property, typically when you get this kind of a relationship from the rule of mixtures, you can be assured that even when you go to more and more advanced models, you're not going to have so much of sensitivity of that property, composite property, to the fiber volume fractions. Yes, when you go very close to the fiber volume fraction of 1, or let's say its theoretical limit over here for a hexagonal structure, then you could have that, but those are very rare situations, and we have other issues, as I said, where the fibers are getting too close to each other, the shear transfer is not taking place properly through the matrix. So you would typically be operating in this range, and therefore it's the choice of the matrix which will to a large extent determine how much your Young's modulus is going to be in the transverse direction. Why it is so, we will see shortly, but any questions or doubts on this? Yes.
Sir, if we look at it, general volume fraction limits of 0.4 to 0.6. So if we look at 0.6, then that means that if I take any cross section, only 40% of the area will have the matrix in it.
60 will be matrix, 60%, 40% fiber.
So 0.6, we have 60% fiber and 40%
Yeah. We have 60%, yeah.
So 40% will be the matrix.
Correct.
And then any transfer that should happen between two fibers
Mhm.
should go through the matrix.
Correct.
And the matrix, the fiber would generally have far higher Young's modulus than what the matrix would have.
Mhm.
Then how does that load sharing happen? Because only 40% of the area should now transfer the rest 60% of
Yeah.
the stress,
Yeah.
and with much lower Young's modulus than what the other one has.
Right. See, if you plot the stress versus strain curve, stress versus strain curve for this, you typically have, I'm going to do for the fiber, the composite, and the matrix. So the fiber we know has a very large strength that it goes to, and a very large modulus as well, which is what we calculated over here, the EL, right? So the therefore you're going to have a curve something like this. Let's say it's a brittle material, so it essentially fails at a stress like this, and the slope of this would be equal to your E longitudinal of the fiber, which is what you have over here, or ELFs. I'm interchangeably using subscripts and superscripts, but that is what you understand, I think. So then, on the other hand, if it's a polymer matrix, you know that typically for larger, it can take much larger strain. See here, the failure stress is very large, but the failure strain is very, very small. So that's what happens. Whereas in the case of the matrix, you would have much lower modulus. In other words, your EM is very small compared to ELF. So essentially it will go something like this. It can have a fairly large nonlinear portion also, but essentially it will fail at some location over here, which is going to be fairly large compared to this. But the maximum stress that it can take is much smaller. Now, you're saying that I'm having only 60% of the fibers and 40% of the matrix over here. Now, once we calculate this, you would see that the slope has to be lying somewhere in between these two. So it essentially will go through something like this. So it all depends. Right now we are looking only at the modulus. We are not looking at the strengths. It's a much more complicated thing because we have to look at the actual failure mechanism of how the fiber fails, how the matrix fails, or the interface fails, etc. So all of that will come into that. The more reliable models there are the what are known as the phenomenological models. You actually have to look at the damage phenomenon in order to understand how exactly it happens. But there are also very crude ways of estimating that using the same formula. So instead of E, I can substitute sigma UTS, ultimate tensile strength, for each one of these and still calculate that. It will be of the order of magnitude, it will be all right, but you will have a fairly large variation when you actually experimentally test the specimen with the composite. Now, what really is required is that you have a fiber over here and you have an adjacent fiber over here, and there is a matrix sleeve in between them, right? So now, let's say the stress in this fiber is some sigma L F, which we'll call as 1, and the stress in this is slightly different, sigma LL, let me not call it 1, let me just leave that. So a very small change, because these are adjacent fibers, they'll have more or less the same stress. It's only a slight difference because it's actually a much larger structure that we are dealing with. Within that, we are taking just two adjacent fibers. In a cross section, you could have thousands or even millions of fibers depending upon the size of the cross section. So we are just taking two adjacent ones. So just like this is of the order of a few microns, this could also be of the order of a few microns. Again, depends upon the volume fraction. You can actually calculate that, but it will be of the same order of magnitude as the diameters that you have over here, right? Now, it is this change, that delta that you have between one fiber to the other, which has to be taken in the form of shear stress between these two. So it's not the overall stress that is being taken as the shear stress. It is the difference in the longitudinal stress in two adjacent fibers, which is a fairly small amount, which is creating that gradient. But you have the distance also is of the order of a few microns. So not only is the difference between the stresses small, but the distance between them is also fairly small. So you will have a reasonable stress gradient, but that is something that can be handled by the fibers. So if you actually look at the volume fractions and then work backwards to see in terms of the diameters and the distance between two adjacent fibers, you will see that this shear stress that is generated within the fibers for a given typical delta sigma that you have would be within the shear strength of that matrix. So it doesn't matter whether you're having lesser amount of, in this case, only 40% of fiber, it just doesn't matter. But what we are looking at is the ability to handle those differences in stresses rather than the actual stress. Your sigma LLF will be very large. If you apply that amount of shear stress on the fiber, obviously it's going to fail. But the stress that it needs to handle is only the difference between the stresses of adjacent fibers, and that is a fairly small quantity compared to your sigma LLF, and that is handleable. So in fact, you can derive the equations, differential equations, ordinary differential equations that you can derive and solve them and show as a function of this sigma LLF and how it varies along the transverse direction, what is the value of the sigma in the matrix, let's say tau, the shear stress in the matrix, that you can actually calculate, and you will see that it's not very large. Okay, so it's very we are talking because we are talking of rule of mixtures. We're trying to oversimplify everything. So we think that in terms of the percentage of stress that needs to be carried, also one is carrying much more stress. Almost the same stress, because 40, 60, almost 50%. Let us say we are talking about taking. No, it is not doing that, because you know that. You can load the whole structure somewhere up to here also. In other words, the composite is going fairly large. But what will happen is, typically at that value of the strain at which the fiber fails, that is all that you're actually going to utilize the matrix for, because beyond that, it's just the matrix, the fibers have all gone. So then it's not going to be of much use. So this entire range that you have is not going to be of too much of a significance. It's in terms of the final failure, because already you have taken the load in the composite to a fairly large value, and then the fibers have failed. Now all of those load which was taken by the fiber along with the matrix have to be entirely taken by the matrix, and that's going to almost immediately fail. So once all the fibers fails, you are retaining that kind of a load over there. It's almost instantaneous that the matrix fails. So this portion is anyway not going to be of much use, except in the fabrication, whole fabrication process, the liquid or semi-solid nature of the matrix makes it very easy to put your fibers there. That is essentially in the pre-preg fabrication rather than the structural fabrication. In the structural fabrication, you already have a partly cured matrix, and still you have a certain amount of liquidity that is there in that, or ductility if you want to call it. But so that can actually be utilized in much more proper arrangement of your fibers within that, or across two layers, how you want to arrange, and then the curing that happens between that. All of that can be taken care of. But do not use the assumptions that you're using for the rule of mixtures to oversimplify what is going to be happening over here. You need a little more rigorous model in order to be able to understand this. You can't just divide because it is 60%, 40% fiber and matrix respectively. The 60% load is taken by the fiber and 40% load is taken by the matrix. No, it's a little more complicated than that. Yeah. Yeah. Go ahead.
Basically, my question was more on when a fiber terminates.
Okay, okay. So let's say, so there is a termination of the fiber over there. So what will happen is, see, in this portion you would have this stress sigma LLF that is there would be anywhere in the intermediate. But as you approach closer to the end where it is broken, you would have that stress equal to 0, right? So then you would have to transfer that between the adjacent fiber. So then, yes, there will be a stress gradient which is of the order of your sigma LLF times that, right? But now it's not just this one fiber that is there. Around this fiber, there are many other fibers that are there around this. We are just showing for schematic purposes just one adjacent fiber to the broken fiber. But there are many fibers around that, and it gets distributed between them. So in other words, the entire stress need not be taken by them. And also, this 0 will grow to this over a certain length. It is not going to grow immediately. It's actually exponential, but it will grow to start with over like this, and it will become the same sigma LL over there. So there is a mechanism over there. Without those equations, it's a little difficult to explain that. We will consider those equations in the course on analysis and design of composites, so where we actually derive those equations and show that it is still within the admissible limits. Yeah, but it's a very good question. You brought that up with the broken fiber.
So then does that mean that the longer the fiber I have, the higher volume fraction I can go to? Because if it's a shorter fiber, there will be more terminations happening cross section. Is that how I can interpret it as?
See, the longer fiber composite, the advantage that you have is much more control over the orientation. You see that there's a huge difference between how it behaves, not in this, but when we saw earlier plots where we plotted versus theta, and we saw how drastically it drops in many cases. So when you have shorter fibers, you cannot have too much control over aligning it in a particular direction, which is the preferred direction, because you know that the structure that you're going to build out of it has loads predominantly in that direction. So you want to put the fibers in that direction. Whereas when you have longer fibers, much easier to ensure that they are going to be in that particular direction. So that is where it really helps. But in terms of the volume fractions, it's all a question of the affordability, how much of fibers and matrix you typically have, because shorter fibers are typically used in low-cost applications. So you want to use that, and also in terms of how it gets distributed to ensure that those strong pockets are not there, which are matrix rich or fiber rich. But in terms of the actual volume fraction, it will be more dictated by the affordability of that particular structure. So whether you can have larger volume fractions compared in two cases, one is long fiber, short fiber, there's no particular reason why one can have more than the other purely from a technical point of view. It's all a question of how you disperse that within the matrix.
So for example, if I take a cross section and if all fibers are terminating in that cross section, the strength of the composite will just be the strength of the matrix.
Right.
If I have longer fibers having the same volume fraction, there will be lesser ends.
Correct.
So wouldn't that
Yeah.
mean that?
Yeah, so that's why I said we don't want to have those rich pockets of matrix or fiber. So yours is a classic example of where there will be a matrix rich region where many fibers are ending simultaneously. But the way the short fiber composite is made in different situations, let's say a bulk mold composite where you have a bunch of fibers, let's say like a ball you're putting into the matrix, the mixing process takes care of that distribution to a large extent. But theoretically speaking, it is possible that if the fibers are all ending at a particular location close and then there's a matrix rich region, it will fail there. So there is a huge risk involved with that. That's right.
And the possibility of that will be larger for a shorter fiber.
Correct, because more ends are there. Sure. Yeah.
So what he's saying that if there are shorter fibers, then there should have been a region where lots of fibers are ending. So can we see this diagram?
This one?
No.
Okay.
That as a complete beam with a reinforcement. Okay. So what we can do that we can if one fiber is ending at a distance, if we start another fiber at that point, then there will be a discontinuity. Instead of that, we can start a little earlier, so that at any cross section there will be no
Sure. Yeah. So as long as you have a certain amount of control over the dispersion, how you distribute the fibers within the matrix, you want to keep it such a way that, because it's a random distribution that you're having in a short fiber composite, you want to have it as uniformly distributed as possible. So these things will be taken care of. So what you're essentially saying is that you have one fiber which is ending over here, the adjacent fiber starts over here, so that there is a kind of an overlap that is happening over there, right? So once you have sufficient amount of fibers of this kind of a volume fraction typically that you're speaking, and you ensure that you're distributing them randomly and have a good mix of it, so that there are no very severe pockets which are rich in either one, which are large in size beyond, let's say typically the orders of magnitude which are used are of the order of the fiber diameter or a toe diameter, etc., to measure the richness of a particular component of the composite. So when you have that kind of a distribution with these kinds of volume fractions, these are things that will automatically be taken care of. So you don't need to specifically ensure that, and it's very difficult to specifically ensure fiber to fiber whether the overlap will happen or not. As long as you have a reasonable amount of fibers, you would be good enough to do that. It might be that the fiber cost is not as prohibitive as in the long fiber composite, so you might even stretch this limit to a little more to ensure that these matrix rich pockets are not there. But also you have to ensure that there are no fiber-rich pockets also. So the dispersion has to, there are many different techniques by which the mixing is done, because you also have a certain level of viscosity in the matrix, and it's not like you can very easily do that. So the viscosity to a certain extent will help. Beyond a certain level, the viscosity will actually be a detriment in terms of the uniform mixing that you're going to get. So depending on the specific matrix and the fibers that are involved, the sizes that are involved, etc., you will have different mixing techniques to ensure that it's as uniform as possible, and therefore these kinds of things are taken care of. So you're right that if I have control over whether I have this kind of a design or some other equivalent where I have two fibers like this, obviously this is a better design and this is not, right? So I would try to ensure that this happens, but it's very difficult to do that for individual fibers. For what the example that you gave in terms of concrete reinforcement with the rebars, the steel rebar, there you know how you can tie up those rebars, so you will have overlaps, and that is very commonly used in beams and columns, even the the roof slabs and things like that. So that is ensurable. But here we are talking of order of a few microns over here, 7 microns or something like that, micrometers. So you're it's very kind of difficult to get that each of these things verified. But there are NDE techniques where you can actually visualize what is happening. So when you're trying to develop certain mixing techniques, you can create specimen, and you can actually do let's say an X-ray or whatever to understand how the fiber distribution is taking place, and see if certain changes to your mixing process can probably improve that. So those are things that can be done to improvise that. But once it's established that this is a reasonably good mixing process, they continue with it without having to check, except for a few samples through the manufacturing process. Yeah.
In that case, the schematic, when there is a lateral force is applied, the propagation of stress, it first encounters a matrix, then it goes to the fiber.
Correct.
So
Correct.
100% load is carried by the
Correct.
matrix,
Correct.
and then it is transferred to the
Exactly. Yeah.
fiber.
Correct.
So they, if we look at the carrying capacity of in the strength capability of matrix and fiber, there's a huge gap.
Correct.
So we always try to ensure a smooth propagation of stress towards the material, but in this case there is a reasonable gradient, a reasonable gap is
Correct.
creating. So
You're absolutely right, and in fact that is what we are seeing over here. When you go to the transverse here, not even when talking about strength, even the modulus for that matter, it is matrix dominated. When we go to the strength, that the corresponding strength, that is the strength in the transverse direction for the composite, which is the ultimate tensile strength for this, then you would see that that is also highly dominated by the matrix. So in other words, once the matrix fails, you're not going to have much of the load carrying capability, because the fibers can't do much in the transverse direction, which is why that laminate design is so very important, where you orient the fibers in such a way that you know there are certain dominant loading directions, but there is a possibility of off-design loads coming up. So you ensure that there are fibers in those directions also. May not be as much same thickness in the layers overall compared to the 0 degree along the loading direction, dominant loading direction, but you ensure that. So you cannot do it at this level where you're now looking only at the micromechanics, a single fiber and a matrix sleeve around that. Yes, the matrix is the weak link over there. But then by reorienting that, instead of the same thing, this is the load. Now I know. So instead of having the fibers this way, I'm going to put one more layer which is going to have fibers this way, one more layer where there are fibers this way. So this is automatically taken care of by those layers which are closer to 90 degrees rather than this layer. Okay, so you have to redistribute it in that particular fashion. So right now, because we are focusing only on the micromechanics, it might seem like this is a disaster. Yes, it is. if you had, let's say, all a 0-degree laminates and there is an off-design load that comes up like this, it's going to be failing at very low stress. So that will be an inappropriate design to have. So when you're talking of the design, you're building up this material and the structure simultaneously. You're choosing the fiber, you're choosing the matrix, you're choosing the volume fractions. That is not the end of the story. You have only designed one layer out of it. That layer, which orientation you're going to put in and how many other layers you're going to put in, what are the orientations of that, that's when you develop the overall material and the structure. So by having a priori information on the typical kind of loading situations that it can go through, there may not be one load. There could be many different loading situations, loading scenarios, depending upon what maneuvers and other things that the aircraft might be performing. It could be a taking off, landing. It could be even taxiing. Sometimes some structures might be critical. So you have to ensure that for all of those situations, what are the kinds of loads that are going to come on individual composite components, and ensure that there are sufficient amount of fibers to take care of that. It may not always necessarily be a 90-degree fiber, even a 45-degree fiber. Sometimes if the load of design load is a very small of design load, it might still be able to withstand that. But you may not, as long as you know that there are going to be off design loads in a particular direction, to go with fibers, all the fibers perpendicular to that, is going to be usually a very bad design. Yeah. So anything else? Yeah. So maybe I'll try to see if we can. So one part of the homework is to use the same approach that we did, but to derive the Poissons ratios. So these might, the symbols might look very similar, but this is new, which we use for Poissons ratio, and this is small v, which we use for volume fractions. But you see that the relationship is very similar. It's like, for example, putting, I showed springs, but you could even think of resistors. Two resistors in parallel to each other is essentially a series. So whether it is the Young's modulus in the longitudinal direction, or the Poissons ratio, which is in the longitudinal transverse direction, it follows very similar rule. In other words, if you plot versus the fiber volume fraction, you're going to get a straight line. It's a linear dependence on the fiber volume fraction. So I would like you to go through the same approach and write it down. These are things that are even available in a lot of textbooks and other things, so you can just copy it. But what is important for me is the step-by-step approach, and at each step, what is the assumption that is involved? What takes you from one step to the other? There could be a lot of hidden assumptions which many textbooks also would not probably state explicitly. So, or might have stated much earlier than where you're looking at the derivation. So I want you to go through that process, some of which we visited when we derived that. We talked about a few of those assumptions. Similarly, I want you to derive this. Now, there's one more thing that I want to talk about here. A single subscript was good enough over here, whereas here you need two subscripts, because the Poissons ratio is involved with applying the strain in one direction and measuring the strain in the other direction. And the ratio of that with a negative sign is what we call as the Poissons ratio by definition. So in this notation, in isotropic materials, you didn't have this problem. But now that you have an anisotropic material, a composite, there is a difference between which direction you are applying the load or the strain, and which direction you are measuring the strain, right? So in this case, always we will follow the convention that the first subscript will be the input and the second subscript will be the output. So in other words, let's take the example of this. In this case, this is along the length is the longitudinal direction, perpendicular to the length is the transverse direction. So what I'm trying to do is I'm pulling this apart by a certain amount of strain and measuring the strain in the perpendicular direction. I'm dividing this strain by this strain with a negative sign. I get that. So in other words, this is capital gamma LL divided by, capital gamma TT by capital gamma LL. Let me write it down. So this is defined as So we use this symbol typically to refer to definition, that is a triangle above the equal to sign, and this is defined as your output, which is gamma t. Gamma tt by your input, which is your gamma ll. So in other words, you're extending it by a strain gamma ll, and you're measuring with a strain gauge the strain in the other direction, taking the ratio of that and the negative of that. So that's how you define nu lt, whether it is for the composite over here or it is for the fiber over here, which in general could be anisotropic, and therefore it needs to be mentioned, whether LTU needs to be mentioned over there. And this is usually isotropic material, the matrix, so you don't need to mention LT explicitly over there. So this is what you have. So also make sure that this is nu and this is small v, so that you don't get confused between these symbols for the volume fraction and the Poissons ratios. Okay. So I think with this probably we'll stop. We will take up the other example. I already did a plot for you of plotting ET versus the fiber volume fraction, which was not linear, but it had a huge drop. It had a huge increase, right, going from this side. So it had a huge increase, and that we will derive that equation in the next class, and we will take it forward from there. Okay. So there will be certain other parts to this homework. So right now you can just focus on this part. We will come to the others later. Thank you.